Hi everyone, welcome to this virtual talk. I am Berta, a fellow at CERN, and today I will talk about the work I have carried out together with some of my colleagues from the fire safety engineering team at CERN, Jordana Guy, Oriol Rios, and Sabrina Mendla, in the context of a project called FIRIA, in which we have modeled and analyzed using FDS one of the largest underground caverns of CERN's LHC Accelerator complex. So before I start with all the details of the analysis and the challenges, let me briefly introduce you to CERN. So as some of you may already know, CERN is the European Organization for Nuclear Research, and as such, it is a particle physics laboratory that houses the largest accelerator complex ever built worldwide. In fact, here you can see in the screen a drawing of the Large Hadron Collider, the LHC, on top of an aerial view of the region where CERN is located, in between Switzerland and France, and some of the main points or highlight experiments and sites are highlighted. And so I will be presenting an example of a model of one of the caverns of the LHC that you see here, and so that you get an idea of the installations and the environment of this laboratory. It houses around 45 kilometers of underground tunnels, around 800 buildings, and it can be quite challenging, especially because of the nature of the experiments that are carried out here. Some of the combustible material present in these facilities, such as cables, racks, pumps, etc., can be radioactive. And this means that the smoke that could potentially be produced and then released to the environment could be activated as well. And this poses a challenge that we cannot neglect. So in this context is where the FIRIA project comes in, because FIRIA stands for Fire-Induced Radiological Integrated Assessment, and it's a project that was launched in 2018 by the HSE unit at CERN, with the aim of developing a methodology able to assess both the fire risk and the fire-induced radiological release risk that can be encountered in particle physics laboratories and the facilities that we can find here. So in a nutshell, I want to very quickly introduce on the key steps that explain a bit the next slides that I will be showing. When carrying out, let's say, a FIRIA assessment, one of the first steps of this methodological system, analyzing what are the key scenarios we want to analyze of a certain facility. We choose a facility we're interested in. We choose a series of representative scenarios. Then we carry out some fire dynamic simulations in which we try to understand the amount of soot produced, and out of the soot produced, how much of it would be deposited, how much it would be released, etc. And then a series of environmental dispersion simulations would be carried out in order to then determine the dose assessment and the impact in terms of activation to the environment, etc. So these are very, very quickly and just briefly all these steps, but I will focus on the first part. So for a specific facility and a set of scenarios, we carried out a series of FDS simulations of one of these most complex facilities we could find or we can find at CERN. And this is the case study I'll be talking about. So this is the zooming of the detector, or one of the 4 detectors that can be inside some of these experimental caverns of the LHC I was mentioning before. And as you will see later on, we were able also to introduce or to include in our model a model of this detector, which it was a very nice opportunity also for the high level of detail. It allows us to determine where the soot would be deposited, which property or which equipment should be taken care of, etc. So it really also allowed to push to its limits the computational resources. We have been using the high performance computing cluster in which we are running our simulations, etc. And you may wonder the reason why I'm saying this. So let me first introduce you in this case to the complex of caverns. So I will just focus on what I called here Cavern A. It's the cavern where the detector is housed, and it's connected to a surface buildings via two shafts. I think I should highlight that this cavern is located 100 meters below the ground, so below surface level. And it's around 50 meters by 50 meters by 30 meters. So, I mean, it's really a huge volume. And we wanted to know, first thing, if we had to analyze and model it all at the same time in FDS. Because you see on the left, it's a simplified voxelized FDS model of the same complex. And luckily, we discovered that the possible leakages that we could find in between caverns or in between buildings were not significant enough. So the order of magnitude made it not worth it to model it altogether, because here we are dealing we would be dealing with way too many cells. It would take a lot of time to carry out these simulations. So we decided to treat them independently. And independently, in this case, means that we are treating, for instance, the experimental cavern with its two shafts and the surface building when these two are connected. And inside the experimental cavern, the other, let's say, we can call it big achievement, was the fact that we were able to include a model, a pre-existing CAD model of the detector inside our FDS model. And then this would allow us on the post-processing to determine if specific areas could be damaged because high temperatures were achieved, or if a soot that would deposit somewhere critical, etc. So for us, it was also really important to be able to make this as accurately as possible. And the other interesting point that we had to decide is which boundary conditions we would be considering for the experimental cavern. So mainly we have, of course, let's say the boundary conditions of the domain, but here the fact that it's the surface building, the one that's connected to the outside, to ambient, we wanted to see if also the conditions or the ventilation conditions of the surface building could have an impact on the fire dynamics of the underground cavern. And here there are two main cases. So the case on the right, it's what I just called here run, because it's referring to when the LHC is in run mode. So and in this case, there's no influence whatsoever of the surface building, because it is completely isolated from the underground one. However, when we are in shutdown, so the LHCs turn off, their maintenance activities being carried out, then we have to consider as well if the surface building can have any type of influence. There's different doors that could be open, closed. There are also different ventilation points on the ceiling, forced, natural. So it was important to determine, because otherwise we could have many more cases to analyze. We already were considering a significant number of scenarios, but then we would have to multiply those by the number or the amount of time and the number of cases in terms of geometry we wanted to test. And so you can get an idea, one single of these cases was made out of around 12 million cells, and it took to run in almost 800 CPUs in parallel around 2.5 days. So we had to choose wisely which case we wanted to consider. So in the end, it was corroborated that the ventilation conditions on the surface building itself did not have an impact on the fire dynamics of the cavern. However, the mere presence of the surface building was interesting in itself. Here you can see an example of some of the results. This is a velocity slice, and you can see how the air is behaving in the, let's say, in the complex. And another point I would like to show is the fact that, so I mentioned we were interested in the fire hazard and in the fire-induced radiological risk, which is associated to the amount of soot that would be released. In this case, we could see it as the orange area, and how the ventilation conditions on the cavern itself can have an impact also on the amount of soot produced, released, etc. So for these several ventilation conditions for the same geometry and same fire scenarios were tested, trying to analyze the impact. The case shown as an example here is a bit obvious in the sense that if the cavern is in run mode, so everything is sealed, it's not connected to the surface building, and the ventilation is turned off, then we can see that no soot would be released to the environment. However, there were also other aspects to consider, such as the temperature, the pressure achieved inside, the amount of soot deposited, where the soot is deposited, etc. But just to show that this is a magnitude we're very interested in, and in order to validate our model for every simulation run, we would always carry out a mass balance check. And yes, this is all for the results and the overview of the model. It was quite quick, so I'm available for your questions. Thank you very much.
Yeah, so we have a good question here. So Dave, Stacy may have missed it, but how did you quantify the fire scenarios themselves? Was it electrical components, fuel, etc.?
Yeah, so that's a good question. It was a mix, so there were several scenarios. Some of them was cables, there was also some of the fuel, oil, etc. And depending on the scenarios, some of them were characterized based on literature, some others based on the tests we carried out. So with all this information put together and based on what we observed in the facility when we went to have a look, we decided how to choose that.
Interesting. Cool. Thank you.
Yes.
Let's see if anybody else has any questions. I wondered what kind of like supercomputer that you needed to run that calculation. It looks really interesting. Yeah. You probably have access to all kinds of machines at CERN that have a few processors.
Well, yes, we have this high performance computing cluster, and of course we have support for that because we need someone that is in the background supporting us with all the libraries and so on. So this is what we use to run the model.
Did you run into any issues running on 800 processors?
I don't now. It doesn't come to the top of my mind. Like we did. So this was not the first. Like we didn't start with this model. You see, like this was one of the biggest ones we run, but we didn't start with this one. So we tried to solve all the possible issues, and we tried to also optimize in terms of the resources used, MPI, parallelization, etc. But
okay. Antonio has a question that I think would be better for Kevin McGrattan's talk when he talks about recent new developments in FDS. Okay. So that Antonio, if you want to ask that, or maybe Kevin, get ready to answer, but it has to do with computing and CUDA cores. So it's a little different topic there. Did you check consistency of your results?
I'm not sure what do they mean by consistency, but like, I mean, we tried to do some validations. These, for instance, towards the end in my presentations, I saw our mass balance. So for us, taking into account the amount of soot release and produce and so on. So we wanted to make sure that all that added up. So that was one of our key, let's say, checks that we could carry out with this regard. I think this is one of the most important one, I would say.
And kind of a follow-on to that, did you run any experiments to validate the soot deposition in your scenarios and how that might impact the results?
No, it would have been nice, but let's say, but no, unfortunately, we didn't. We don't have any soot deposition. That's
great. It looks like Wojciech is sharing a link. An awesome recent resource about this. So was there a paper? This is like a published paper or something on this, I think. Yeah, that's what he's linked to. Thanks for that. And we will have your paper and your slide deck available on the archive page and your talk page after the event. So people can follow up there. Ernest has a question. Did you do your analysis on the cluster smoke view, or did you import the results into PyroSim? He asked because he seems to lose some components during transfer from the cluster to something like PyroSim.
Okay, so to analyze the results of the simulations, I guess. No, we did that on SmokeView, so we didn't import the results and open them in PyroSim. So we use PyroSim to basically import the pre-existing cut model of the detector, which was huge and that was super useful. But then to do the post-processing afterwards, we use SmokeView and also some dedicated Python script to make it a bit faster and more clear.
Okay, great. Yeah, and I would be interested in, Ernest, what you've seen. So if you try to open up the output and results, so maybe that's something you can send in another channel. Kevin did answer here, just a quick answer about CUDA, that they have nothing really on that going on at the moment. They're interested to see if CUDA could significantly speed up calculations. So again, that would be a great conversation in Kevin's chat and maybe a follow-up with them directly. I am aware of some work in that in the past and some people making some issues. I think it's come down to issues with pressure solver across multiple meshes, but maybe that's less of an issue. And we do have a talk later in the event about different pressure solver implementations too. So that would be good from Susanna Killian. So,
very nice.
Oh, what is CUDA? Eric asks. It's like using GPU cores for computational power, not just CPUs on your motherboard. So in many of the graphics processing units, they have hundreds or thousands of cores, of little processor cores, and so using those instead of your CPU cores. Okay, so next talk is going live. I just want to say, let me see, did you do any mesh sensitivity study or a good way to decide the mesh size?
Yeah, we didn't do any mesh sensitivity study, though it would have been nice, but also the model was huge. We had lots of time constraints, but we have done it for other models. So this is based on what we chose our mesh size or our cell size, I would say, yeah.
Okay, great. Well, thank you for that. Thank you for the presentation and the great Q&A, and we'll switch over to the stage and continue there.
Thank you very much.
Bye.
Bye.